Okay, so we're going to talk about light. And light, as you know, is also known as electromagnetic radiation. So what's an electromagnetic radiation? Uh, Electromagnetic has to do with the fact that it's associated with charged particles. Okay, so behavior of light can be explained as, from Maxwell's work, as an electromagnetic wave. Okay, so the idea is this: if you have a wave is a periodic disturbance that propagates through space. Okay, so it's a repeating disturbance. That's what periodic means. Okay, and electromagnetic, that adjective just tells you that it's got something to do with charged particles. Light is produced by oscillating charged particles. Okay, and a wave is, like I said, it's a disturbance. It's basically a way for energy to transfer from one point in space to another. Okay, so like imagine you were to drop a rock on a pond. What happens? You get ripples of water emanating from where the rock fell, right? So you have a wave. What would happen if you have something like a cork somewhere away, a few meters away from the rock, from where the rock fell? Once the wave passes it, what happens to the cork? It ends up bobbing up and down. So you've transmitted the energy of the rock to the cork. So the wave is the mechanism by which energy is transferred from one point in space to another. Okay? So exactly what is it that's waving in an electromagnetic wave? It would be electric and magnetic fields. And just to review your physics, an electric field that's the coulombic or electrostatic force that a charge of 1 coulomb would feel at a given location. So the electric field is, the unit for it is newtons per coulomb. Okay? And it's strongest at the crest of the troughs. Okay, so a wave like this you can represent it by a sine wave like this. Okay, and at the crest, this right here, the magnitude of the electric field is strong, most positive. That means a charged particle at that location would feel the strongest force directed upward if it's positively charged. And at the trough right here, at this particular location, the force that a charged particle would feel would be downward, right? That would be strongest. So that's a trough. This is the crest right here. And where the force, the locations where the particle doesn't feel, a charged particle would not feel a force would be what we would call a node, right? Now, the magnitude of the electric field at the troughs or the crest, this magnitude right here, okay, this value of the electric field at the crests and the troughs, the magnitude of that is called the amplitude of the wave. Okay? Now, the magnetic field wave is perpendicular to the electric field wave. So if this was like the xy plane, let's call this the xz plane. Okay? So if this is the z-axis, and this is the x-axis, okay, your magnetic field is going to be oscillating like so. Okay, it would be on the xy plane. Okay, let me show you an animation that shows that better. Let me see. Animation, electromagnetic wave. Right here. See, you got an electric field, okay, and then perpendicular to that, you have a magnetic field. Okay. So let's do a quick check here. Here's a snapshot of the electric field component of an electromagnetic wave as it travels through space. At which of the locations indicated here would a charged particle experience the strongest force? At point A, B, C, or D? A, because strongest force in which direction? In the downward direction, right? That's if you have a positively charged particle. Of course, if you have a negatively charged particle, the force would be the other way. Okay? And B and C are right around the node, and D is not quite at the crest and not quite at the